Today we are presenting special requirement for aerospace material by Group 18. That is our teammate. Aerospace material are those materials specially chosen for the use of aircraft, rocket, and satellites. With that extreme purpose, material using need to be facing the following scenario. So let's move into the first scenario, which is lightweight and high mechanical strength material. Lightweight, lighter the aircraft gives the greater the efficiency both mechanically and economically. And high mechanical strength is definitely required because aerospace cannot split into apart in the space. Advanced aerospace material achieve both by clever use of atomic structure. Moving on to two categories of material that achieve these two characteristics. First is aluminum and titanium alloy. Base material already have relatively low density, and alloying with elements basically strengthen it as a solid solution strengthening. Alloy atom destroy the crystal lattice hidden in dislocation motion, and this material commonly used as the cover of a rocket. Secondly is carbon fiber refined polymer. Carbon fiber made of graphite structure with strong covalent sp2 bond along the fiber axis and has very low density. Polymetrics hold fiber together, transfer load at softness, and those materials used as the thermal insulator.
Thank you. Now I'll be talking about electrical materials used in aerospace, specifically focusing on three categories: conductive, inductive, as well as electrostatic resistant materials. Each of these plays a vital role in ensuring reliability, safety, and performance of modern aircraft and spacecraft systems. Let's start with conductivity. Conductivity is the ability for a material to let electrical flow. In aerospace, this property is extremely important, especially for lightning strike protection, grounding system, and electrical wiring. Materials with high conductivity like copper or aluminum ensures electrical flow safely where it's needed. More importantly, it prevents dangerous buildup of static or stray currents that could harm equipment or crew. On the other hand, we need materials that resist electric current, and that's when insulation comes in. Insulation protects the system by preventing short circuits or electrical breakdowns, especially in high voltage and sensitive components. In aerospace, this is even more critical because in high altitudes, even in vacuum environments like space, arcing and electrical faults are more likely to occur. Insulation materials help keep systems safe, reliable, and separated from one another. Now, let's talk about electrostatic discharge or ESD. ESD happens when buildup of static electricity suddenly jumps between objects of different charges, like a mini lightning bolt. This might sound minor, but in aerospace, it's a serious issue. Satellites and spacecraft can get charged by solar winds and plasma, and without protection, ESD can cause arcing, damage circuits, and even sparks explosions.
Okay, now let's dive into the heat-resistant materials used in rocket systems. First, let's have a look at the main systems of a rocket. A rocket is made up of four main systems: the payload system, which carries the cargo or instruments; the guidance system, which controls the rocket's direction; the propulsion system, which generates thrust; and the structural system, which holds everything together. In the payload system, ceramics like silica tiles and composite like pica are used to protect instruments from heat. The guidance system uses polymers such as Kapton and PTFE, as well as ceramics for electronic insulation. In the propulsion system, materials face the most extreme temperatures, so alloys like nickel-based superalloys and ceramics like zirconia coatings are used. Finally, the structural system uses lightweight yet strong materials like aluminium, lithium, and titanium alloys, along with composites and ablative polymers for extra protection.
I'll now move on to material fatigue. Materials in a spacecraft undergo repeated cyclic loads due to the different harsh environments that it comes into contact with. This results in failure over time and can lead to disastrous outcomes. I'll be discussing four types of material fatigue experienced. Due to the drastic temperature changes at different altitudes, the spacecraft materials must be able to withstand rapidly changing temperatures. These can go from extremely high to low temperatures, causing them to expand and contract, and can result in damages. Radiation caused by charged particles and ultraviolet radiation can cause the polymer structures to weaken, hence they must be resistant against it. Physical damage from debris, needless to say, may damage the materials, hence it must be able to withstand impact. Lastly, corrosion is a gradual deterioration of the material. The material, if not resistant, can form oxides, which change its properties. Stainless steel with high chromium and nickel content are favored due to their high corrosion resistance. Erosions are caused by atomic oxygen and results in oxides, and they must be prevented using coatings or multi-insulation blankets to prevent corrosions before launch.
Moving on, I'll be talking about smart materials. So what are smart materials? They're intelligent materials with adaptive capabilities to respond to harsh and extreme conditions in space, to which their shape, properties, or functions can be changed in response to an external stimuli. They enhance reusability, safety, cost, and efficiency. I'll be sharing 4 examples. Firstly, I'll talk about shape memory alloys, also known as SMAs. They hold a memory of its original shape, thus able to revert back despite extreme temperatures. This occurs owing to their properties of shape memory effects, superelasticity, and biocompatibility. Nitinol is the most commonly used SMA in aerospace, and it retains its shape through its martensite-austenite transformations. Secondly, we have piezoelectric materials. They're substances which generate electric charge in response to applied mechanical stress. They contribute to structural health monitoring by generating electrical signals when stress or cracks develop, allowing real-time detection before catastrophic failure, thus reducing costs while safety increases. Thirdly, we have self-healing materials, advanced materials that can autonomously repair damages. They function through extrinsic and intrinsic mechanisms whereby healing agents are stored in the material or material heals itself respectively. Lastly, we have ATSP, the bitrimer polymers with unique self-healing and reversible bonding capabilities. They can also withstand high temperatures and also exhibit reversible bonding through interchange transesterification to establish robust adhesive connections. In conclusion, aerospace materials form the backbone of flight and space travel, built to endure extreme conditions while delivering strength, durability, and performance. From lightweight composites to advanced alloys, they drive efficiency, safety, and sustainability. As aerospace evolves, innovative materials will shape the future of flight, empowering the technologies that push the boundaries of air and space. Thank you.